So yeah, I'm going to talk to you about Swift performance. And so when building software, especially mobile software, where people are kind of like distracted and busy, and they want to get on with their life rather than sat looking at your application, it's frustrating when apps are slow and don't do what they want when they want to do it. So it's important to make your code fast. And so let's go. And this is being weird. OK. Cool. So what makes code slow? So when you're writing code and choosing your abstractions, it's important to be cognizant of the implications of those abstractions. So understanding the trade-offs between opting into dynamic versus static dispatch and how things will be allocated and how to choose the best fit for you. So I'm going to start out by talking about those. So allocation. One of the biggest and often unavoidable costs in code is object allocation and deallocation. And Swift will automatically allocate and deallocate memory for you. And there are two types of allocation. Stack-based allocation. And when it can, it will allocate memory on the stack. The stack is a super simple data structure. You push from the end of it and pop from the top of it, as that tortoise is about to do. And because you can only mutate the ends of the stack, you can implement it by just keeping a pointer to the end. And allocating and deallocating memory from it is a case of reassigning that integer. And then we have heap allocation. This is and this allows you to allocate memory with a far more dynamic lifetime, but requires a much more complex data structure because of that. So to allocate memory on the heap, you have to look up a free block in the heap with enough size to have your object. So you find the unused block, and then you allocate that. And then when you want to deallocate memory, you have to search where to reinsert the block. And that's slow mostly because you have to lock and synchronize things for the purposes of thread safety. And so then we also have reference counting, which is slightly less expensive but happens way more often, so is still kind of a pain. And so reference counting is the mechanism used in Objective-C and Swift to determine when it's safe to release objects. These days, reference counting is forced to be automatic in Swift, which means it's much easier to ignore. However, then you look in instruments when your code is being slow, and you see like 20,000 calls to Swift retain and Swift release, taking up like 90% of the time. And so that's because if you have this function that takes an object and does a thing with the object, the compiler will automatically insert a retain and release, so the object doesn't go away during the lifetime of your method. And these retains and releases are atomic operations and therefore have to be slow. Or rather, we don't know how to make them much faster than they already are. And then we also have dispatch. Swift has three types of dispatch. It'll inline functions where possible, and then there's no additional cost to having that function. The calls are just there. Static dispatch through a vtable, which is essentially a lookup and a jump and takes about 1 nanosecond. And then dynamic dispatch that takes about 5 nanoseconds, which isn't really a problem when you only have a few method calls. But if you're inside a nested loop or performing thousands of operations, then it starts to add up. Swift also has two main types of object. You have classes, and with a class, everything will be allocated on the heap. So as you can see here, we have a class that is an index, and it has two properties, a section and an item. And when we create that, the stack has a pointer to the index, and on the heap, we have the section and the item. And if we make another reference to that, then we have two pointers to the same area on the heap, and it's shared memory. And we'll also automatically insert a retain for your second reference to the object. With structs, A lot of people will say that structs are the easiest way to write fast Swift code. And that's generally a good thing to have, because they'll try and put things on the stack, and you can often have static or inline dispatch. However, so Swift structs have 3 words of... Sorry, I'm dying. I was trying to get through this without a cough, but... Swift structs have 3 words on the stack for storage. So if your struct has 3 or fewer properties, then the struct's values will generally be inlined on the stack. And a word is the size of a built-in integer on your CPU, and it's like the chunks that the CPU will work in. So as you can see here, when we create the struct, the index struct with the section and the item, the values are just directly there on the stack, and no extra allocation has occurred. But what happens when we assign things elsewhere? So if we assign P2 to P, we simply copy the values that are already in the stack again, and we don't share the reference. And this is where we get value semantics from. But what happens if we have a reference type in our struct? Well, our struct has the inline pointers, and then when we assign it elsewhere, we have the same pointers shared across the 2 structs, and we have 2 retains to the pointers rather than a single retain on the object. And this is more expensive than if you had a class, for example, with the same result. And so, like, as we said before, Swift provides a lot of different abstractions that allow you to make your own decisions about how code should be run and its performance characteristics. So we're going to look at how this applies to actual code. So here's some simple code. We have a circle with a radius and a center. So it has 3 words of storage and will be on the stack. We create 100 million of them, and then we loop over those circles and call a single function. On my computer, this takes 0.3 seconds in release mode. But what happens when the requirements change? And rather than just drawing circles, our code now needs to be able to handle multiple types of shape. So let's say we need to draw lines. So we're super excited about protocol-oriented programming because it allows us to have polymorphism without inheritance and allows us to think about the types. So what we decide to do is extract that out into a protocol. And the simple change of referencing the array by the protocol now makes the code take 4 seconds to run. That's a 1,300% slowdown. So why? This is because the code that was previously able to be statically dispatched and executed without any heap applications cannot be done. And this is because of how protocols are implemented. So for example here, you can see that all we know about is our circle. And so what the Swift compiler will do is either go through the vtable or inline the draw function directly inside the for loop. When we reference it by the protocol, it doesn't know that the object is it doesn't even know that it's a struct or a class. It could be anything that conforms to that protocol. So how do we actually go about dispatching the draw function? Well, the answer lies in the protocol witness table. It's an object with a known layout that is generated for every protocol conformance in your application. And this table essentially acts as an alias for the underlying implementation. But in this code here, how do we actually get to the protocol witness table? So the answer there is the existential container, which, for now, let's say, has 3 words of storage for structs that fit inside the value buffer, and then a reference to the protocol witness table. So here, our circle fits inside the 3-word buffer and won't be referenced separately. But our line, for example, which has 4 words of storage because it has 2 points, and my slide is basically source-kit service terminated. So this line struct requires more than 4 words of storage. How do we do that, and how does that affect the performance of this code? Well, this happens. It takes 45 seconds to execute. So why does this take so much longer? And just why is that happening? And a portion of that time is spent allocating the structs, because now they don't fit in the 3-word buffer. Their storage will be allocated on the heap. But it's also partially related to how protocol works again. So because the existential container only has 3 words of storage for structs, or a reference to an object, we also need to have something called the value witness table. And this is what we use to handle arbitrary values. And a value witness table is also created, and then it has 3 words of storage for the value buffer for any inline structs, and it generalizes allocation, copying, destruction, and deallocation of a value or a class. And so what happens here is so what we have here is an example of some code and then what will be generated from it. So this is if we just had a draw function that took a value, and then we create the line, and then we pass it to the drawable function. So what actually happens is it passes the drawable existential container, and then that'll be created again inside the function. It'll copy the value in protocol witness table, and then allocate a new buffer and copy the value of the other struct, or class, or whatever that object is. And then it'll use the draw function on the protocol witness table and pass it the actual drawable. And you can see that the value witness table and the protocol witness table will be over here on the stack, and the line will be on the heap, and as will the line drawable. So as you just saw, simple changes in the way we model data can have a huge impact on performance. So let's look at some ways to avoid these costs. So let's talk about generics. And you're going to say, but you just showed us that protocols can be really slow. Why would we want to use generics? And well, the answer becomes from what generics allow us to do. Say we have this stack struct that is generic over T, which is constrained by some type, which would be a protocol. What the compiler will do is replace that T with the protocol, or like the concrete class that you're passing to it, and then do that all of the way down the function chain, and can create specialized versions of that code that operate directly on the type. So you no longer need to go through the value witness table, the protocol witness table, and you eradicate the existential container, which can be a really nice way to still write really fast generic code and have the really nice polymorphism that Swift gives us. And that's called static polymorphism. You can also improve a lot of your data model by using enumerations rather than having lots of strings from the server. So for example, if you were building a social network and had a bunch of accounts that needed a status, previously you might have just had that as a raw string on the type. If you had a enum for that, then you don't actually need to allocate anything there. And then when you're passing it around, you're just passing around the value from the enum, which can be a really nice way to speed up your code as well as having safer, more readable code throughout your application. And then also, it can be super useful to have actual domain-specific models. So in the form of view models or presenters or various other types of abstraction that allow you to cut out a lot of the cruft that you don't need in your app. And I think I've ran slightly short, but thank you very much. If you want to speak to me later, grab me in the break or office hours at 16:30 in the atrium. Have some cats.